already had a love of history. And so over time, in fact, like the first PhD thesis I looked at was in the history of mathematics. If you're interested in the history of mathematics, one of the figures that you can't escape is Archimedes. His work is incredibly powerful and set off so many different trends throughout. And if you're interested in Archimedes, it's not long before you come across the name of our speaker tonight, Reviel Netz. He is currently doing what could be described as the first English translation of Archimedes, because he is translating it directly from the Greek rather than trying to also translate the mathematics into modern notation. And he's also been involved in the quite incredible story of the Archimedes Palimpsest. And so it's really nice to see such a wide range of people from across the campus, from English, from history, from the classics, and also from mathematics together to see this event. And so it's my great pleasure to introduce Reviel Netz.
Thanks so much. Thank you. Really. Thank you, Edmund. Thank you so much for inviting me here. You really went out of your way to do this, and I'm grateful for this opportunity. I'm always really moved to see people finding time for the history of Greek mathematics. So thank you, everyone, for coming here today. And I want to share this sense with you, the sense of the passion that this evokes, the sense of the passion of Archimedes, of this pursuit, of this research, a sense of what you can achieve with this kind of research into the humanities. So really it is about what have we learned from the Archimedes palimpsest. It is about those many intersections. It is about many things. It is a story about pursuit, about passion, about the many ways, the many directions that a single piece of research can lead you into. So I will go quickly. I will go quickly in all sorts of directions. All of them intersect, and all of them intersect in all sorts of different ways, all of them coming out of this amazing object, which is the Archimedes palimpsest, amazing author who is Archimedes. So here I start. What have we learned from Archimedes palimpsest? We need to move fast. So, some basic parameters. I want to give some basic parameters for what we're talking about tonight. First of all, everything we know about Archimedes, and this is largely true for antiquity as a whole, comes from medieval manuscripts, okay? They lived about 2,000 years ago, a bit more. They wrote on papyrus. The papyrus usually is lost. We only have tiny scraps of papyri from Egypt. This is not how we know about them, generally speaking. How do we know what they did? We know about it thanks to manuscripts which are about 1,000 years old, if we're lucky, about halfway the way. So we're reading copies of copies of copies. That's how we know about antiquity in general. Now, some of those copies, I want to be clear what was known, what was not. Some of those copies of Archimedes survived and were known already in the 16th century. And when people like Galileo start the scientific revolution, what they're trying to do is to imitate what they find in these sources. Okay, so that's something that was known. Some of it was known, not all of it. More of what we know about Archimedes was discovered in a rare manuscript, in a special manuscript, only in 1906 by this guy which you see right here, which I'll talk about a bit more, the Danish philologist Heiberg, and all of it has been fully deciphered only now. It's only now. So first thing to be clear about, it's only now that we have the complete text of Archimedes, very, very recently. Now, what do we do? What do we do when we are researching these kinds of manuscripts? So the first thing we do is that we collect those manuscripts and compare them and try to recover the original. And you can see even here, in looking at those diagrams, you can see that an original can be recovered. Clearly, here are two separate manuscripts, 1490, 1564, so they are distinct, they are in distinct places, they were copied distinctly, but they share DNA somehow. They come from a single origin. They clearly were copied from a single origin. So what do? You try to recover the origin. Indeed, in this particular case, we know that these are copies from a single manuscript, We know about it. We read about it in various catalogs. It existed, this medieval manuscript, until about the end of the 16th century. This is the main manuscript through which people like Galileo knew about Archimedes. This is how this knowledge was transmitted. This was known already at the time of Galileo, essentially only through copies. The manuscript itself was lost, probably to fire. This is the way manuscripts often die. So here is one important medieval manuscript. We know about it through later copies. It's dead. It's no longer there. So that's A. Now we move to B. B was lost even earlier. Once again, there is a catalog. We know about this manuscript. It died somewhere in around 1300. It exists in the catalog in 1269. It's lost by 1311. In the catalog of 1311, it's no longer mentioned in the Papal Library. The Pope was in Viterbo, and for the Pope was made a translation. The manuscript is lost in this case completely. We don't have a Greek, but there is a Latin translation. There is a Latin translation in this case that survives and is a kind of testimony to what was there. So B is lost. We don't have Codex B. We do have testimony. So we have two separate testimonies by now, but no medieval manuscript. And this is the one extant medieval Greek manuscript of Archimedes. This is the furthest back in time we get to Archimedes. Once again, a distinct source, and this is known as C. And this was discovered only in 1906. By Heiberg, and it takes a genius to discover this one because you can see that it's hidden. Once again, you can see a very similar diagram, not identical, but a very similar diagram, and now you can begin to think, maybe we can take A, B, and C together, combine them, and this way we can get closer to the original. This way we can get closer to what we think Archimedes could have done. But it's not just that. They are different. Sometimes they overlap. The case I shown you was the case of a work that is represented in all manuscripts, in A, B, and C. But in many ways they are different. They are different qualitatively. A has got geometry first, then it moves into physics, and then it has some commentary. C goes the other direction, physics and then geometry. B is just physics and different selections. In all those things there are different selections. They have different selections, different orders, different rankings. They present different images of Archimedes. That's an interesting thought because the image of Archimedes that we have today was shaped by A. Those things are shaped by absolute accidents of here is the book that survived. And this shapes how you think about an individual author. Archimedes was complicated. Archimedes did all sorts of things, we now realize. He did a great variety of things. So we'll get to see them. We'll get to see this variety later on. And one thing, once again, that I want to be clear about. A, B, and C do not cover everything. Even though they don't overlap completely, they still do not cover everything Archimedes did. We have testimonies of other things he did, and surely he did other things besides. We have 11 works, and that's about half of his output. He was a prolific author and a significant author. He approached many fields and did foundational work in all those many fields, more than we have preserved. So that's the basics. That's the basic parameters. And now we begin to pursue Codex C. And in a sense, this is lost. We need science to recover it. The science that Archimedes, in a sense, began now needs to be recovered. We need work today, very careful work, in order to recover Archimedes. I give once again a picture here. She's not an image scientist. She's a conservator. We owe everything to her. Abigail Quant. She's practically the only one who touches those leaves. That's an incredibly fragile document. You don't want to touch it. It really is a cigarette paper thin. It really feels like it would crumble to the touch. You really have to keep it very, very carefully in order to be able to image it, in order to be able to enhance the images and then work from those images and recover from the images. Why is it so fragile? What happened to it? Well, to begin with, it's a palimpsest. The manuscript is a palimpsest. Psao means to scrub. I scrub. Palin means again. Now, how do you make a parchment manuscript? You're working on parchment. So we're in the Middle Ages, we're writing our books not on papyrus, which is a kind of a leaf. We write it on parchment, the skin of animals. Skins of animals, very durable material. You can't write on it directly. You need to prepare it, you scrub it very powerfully. You remove the layers from the skin to prepare the skin, stretch and remove the layers of skin. This is the first scrubbing. This is how you begin to make your parchment. And then sometimes you want to recycle the manuscript. So in 975, a manuscript of Archimedes was made. A copy of a copy of a copy of the works of Archimedes was made. And about 250 years later, this book was deemed useless for a good reason that no one has ever used it. It lay there in the library, no one ever opened it, no one ever read it, and they made a reasonable decision to find a better use for this spare material, which is quite expensive, skins of animals. So what you do is you scrape it again. You go over it again with this knife, and you remove what you don't need. And also, in order that the underlying writing would not matter so much, you fold it. So the writing went like this. You fold it now. And you have a new book that goes like this now. And because the writing goes orthogonally, in an orthogonal direction, it interferes less. So you can see that we changed the very orientation of the writing. Here is how the writing went in the original. Now we're going to write over it in this direction. This is what we're doing with it. So now the Archimedes Codex is made a prayer book. And it's hidden as a prayer book. For 700 years, no one knows what's underneath. And Heiberg recognized what it was. Heiberg made sense of a great deal of it. Not all of it, by no means not all of it. In some cases, this is a double palimpsest. So Heiberg got to it in 1906. He transcribed a good deal, amazingly well, given how difficult it was to read. No digital enhancement, just looking at the manuscript. The manuscript was in better shape back then. So, and this is one of the most radical examples. Heiberg, among other things, took photographs, very good photographs. This is very high quality of photographic art. Took very good photographs that are now preserved in Copenhagen of parts of the manuscript, not all of it. So here is a page of the manuscript as it appeared in 1906, and here is the same page today. What happened? At some point between Heiberg's time and ours, the manuscript was stolen. We don't know exactly how. At that point, we don't know exactly why and how, we can guess, but at some point, some people decided to take some of the leaves of the palimpsest and to use them for forgery. Generally speaking, when you're making forgeries, the real struggle is to find a good material, a convincing material. Everyone can make a convincing Byzantine-like picture. The difficult thing is to produce a convincing 1,000-year-old parchment. So one of the best ways to do this is to start with a 1,000-year-old parchment. So what they did was to take those leaves and to draw, to paint a forgery on them. This is a forged Byzantine illumination. We believe that 7 forgeries were made. 3 were sold, 4 they did not manage to sell 4, and they are still with the manuscript. We've lost 3 pages in this way. We've lost 3 pages of Archimedes. And in some cases, so there are 4 different pages. These 2 are a single opening. There are 4 different pages where the only way to make any reading at all nowadays is through X-ray fluorescence. We bombard this with X-ray. We pick up the fluorescence of the X-ray, which typically reacts to different elements in certain ways. And we find the reaction of the X-ray fluorescence with iron. Iron is an element that you have in the ink that they used in the Middle Ages, not in antiquity. You have it in the ink, you don't have it in the skin of the cow to the same extent. So what we have here is a chemical map of the page, just the iron, and we can read iron, more or less. We can make some kind of reading at this point, but it's very, very difficult at this point. And generally speaking, you can have a sense here of how greatly the manuscript suffered through the 20th century. People very often come to me and say that the church was terrible in destroying the Archimedes manuscript. That's wrong. The church preserved Archimedes' Palimpsest. In the 20th century, when it was no longer perceived as a prayer book, but once again as Archimedes, it was effectively destroyed. Now we need digital imaging to recover it. Now we need all the scientific help we can. So what do we learn? What do we learn from this scientific imaging? So as I said, it leads in all sorts of ways. I think of it as a kind of, well, obviously a treasure box with pieces of jigsaw puzzle. But the thing is that those are very different jigsaw puzzles. You take in a piece and you realize that it fits a different puzzle. Many different pieces help you complete many different puzzles that you were struggling with. So I'm going to describe a few of those. I'm going to describe a few of those pieces and what they fit into. Some of them have to do with mathematics. I'll gradually move into mathematics, I promise. I'll get to mathematics, but we start with something else. To begin with, this is not an Archimedes palimpsest. So it's not about mathematics, it's not even about Archimedes, but bear with me. That's an incredible find. So here is a writing, I think maybe you can even get a feel to it, that it's you realize that what we're reading is not this script over here, it's this very, very faint script going under, right? So this faint script, it feels perhaps already a bit different from Archimedes. It's not Archimedes. Heiberg didn't know that it existed. Heiberg thought that not all of the book contained writing underneath. It was only now recognized that all of it contained writing underneath, and some of it was by Hyperides. Okay, you say Hyperides. What do we care about Hyperides? So I tell you, Hyperides was an associate of Demosthenes. He was one of the great orators of antiquity. He's a famous person, not as famous as Demosthenes, but he was important in antiquity. Indeed, I tell you, we have papyri of him. We have a number of papyri that we dig up of the Egyptian desert. We don't have other manuscripts, but we do have papyri. So we know something about him, you learn. So maybe it's not that important to get the manuscript. But here I think that it completes a puzzle in a quite precise way. Here, bear with me quickly. You can produce the following exercise. As I say, we dig up small pieces of papyri from the Egyptian desert. And that's how we know about the distribution of books 2,000 years ago. And we can look at the question, how many of those authors write in prose and have 5 papyri fragments or more? No one has 5, it turns out, so we have 6 and above. And there is an interesting property shared to all of those. They have more than 5 papyrus fragments, and they have the property that all of them were read not only 2,000 years ago, but 1,000 years ago. All of them were copied into these parchment manuscripts in Byzantium. So what this teaches us is something about what Byzantium did. What happened in the Middle Ages? You could think maybe in the Middle Ages, people had a different set of tastes from what they had in antiquity, and they made their own choices that had nothing at all to do with what people cared about 2,000 years ago. And when you make this exercise, you begin to believe, no, actually 1,000 years ago, Byzantium simply went through the things that were always popular, the things that always matter, the things that matter to people in antiquity itself, and decided to preserve them. And that's useful to know. If this is the case, it's important to know this, because this makes us trust what Byzantium did, what the Middle Ages did, a bit more. This makes us feel that we know about antiquity a bit better through this. So actually, I rather like the fact that this new discovery of Hyperides completes this puzzle. Until we had this manuscript, we had an exception. There was one case of an author that survived plentifully in the deserts of Egypt, but was never copied, as far as we knew, into Byzantium, into those parchment codices. And suddenly you have it. In fact, it was copied. So now we have a complete set. Now we find that if you were in antiquity, if you were important in antiquity, you would be copied into the Middle Ages. That's important. That's important to know. And we know it thanks to this. Thanks to an Archimedes palimpsest. There's nothing to do with Hypereides, with the survival into Byzantium. Well, it does, in a way. It has more than this. I'm saying a treasure box. This is an incredible treasure box, the Archimedes palimpsest, because you open it up and you find Archimedes. There's no other Archimedes. The other Archimedeses are now burned. The other Archimedeses that survive. There's literally no other Hypereides. For all you know, we know that's the only Hypereides that was copied into the Middle Ages. Here is a Porphyry, a commentary to Aristotle. There's another thing, you see. So there are pages that contain Archimedes, most of the book, pages that contain Hypereides. A number of pages contain Porphyry, a commentary to Aristotle. And you can see once again, it's a very different feel of the page, and we need a different digital enhancement techniques, and that's a much harder work. This was the hardest thing to get out of the manuscript in terms of a reading, but it's valuable. Because what we learn now is that there's another unique text. It's Porphyry, commentary to Aristotle, which is not extant anywhere else. So everywhere you look at this book, it has unique stuff. It's a book of unique. So this makes you think, where does it come from? We know, I told you, we know when the manuscript was made. It was made in 1229. How do we know? We actually learned it recently through those X-ray fluorescence. We did an X-ray fluorescence of the first page, which was completely illegible. And one of the things that came up was the colophon, the writing that the scribe introduced when he made the palimpsest. And he said, we dedicate to this city in this year, the Byzantine way of saying 1229. And it's clear from the order of prayers matter in a prayer book. It clears from the order of prayer, from some indications of the writing. We're pretty sure that the palimpsest was made in Jerusalem, in 1229 in Jerusalem. So this makes us think of the Crusades, not 1229, in fact. We're thinking about 1204. In 1204, the Fourth Crusade leaves to the Holy Land, and the knights, the Frankish knights, pass through Venice, and they get into a business agreement with the banks in Venice. The banks in Venice are going to pay for the expedition. They give a loan to the expedition, and then Venetians are going to ferry the knights into the Holy Land. On the way, they pass through Byzantium, through Constantinople, the richest city of Christendom, and everyone suddenly hits upon the clever idea, why don't we just get to business directly? We can sack Constantinople instead, return the loan, and occupy Constantinople, which indeed, this is the fall of Constantinople. This is people always talk about 1453, but 1453 is really the coup de grace for a civilization that has been largely destroyed in 1204, and this is when you have this great sack of Constantinople, when all the works of art are ferried to Venice, where indeed you can still see many of them, when the manuscripts make their great pilgrimage. This is the big moment, not 1453. 1204 is when you have all this massive loss, and it's clear that some of this, much of it gets stolen into Western Europe, other parts trickle away, escape. There are works of art, there are libraries that escape further into the Greek-speaking world. So this is how you get to Jerusalem in 1229. You need to imagine someone who manages to escape with a fine library, but into a very desolate corner of the Greek-speaking world where you don't have the same resources, so you want to create a new prayer book, let's say to celebrate Easter in 1229, but you don't have the resources to pay for a new material, so you use what you have. You use this fine library, and indeed it makes one think, because so in Jerusalem, we think that the Archimedes palimpsest comes from Jerusalem in 1229, and we know it has, besides Archimedes, unique Hypereides, unique Porphyry, and right now, in the library of the Greek Orthodox Patriarchate, there's actually a famous palimpsest produced at the same time a Euripides palimpsest, one of the major witnesses for the text of Euripides. It's not as if there are plenty of texts of Euripides either. So someone is there with Euripides, with Hyperides, with Porphyry, with Archimedes. So one wonders, because this is not a library. It was studied very, very deeply, but we know from the catalog description that there are 4 more palimpsests that are there that were made at about this time. Not all of the writings are currently identified. So I hold hopes for this. You really wonder what might still lie there. And I very much hope that the Patriarchate will get to work on studying those manuscripts. They guard them very closely. They want them to be studied through their own devices, which is, of course, the correct way to do this. And I hope they proceed soon and we'll discover what's hidden there. It may well be that there are more resources of importance. So that's something interesting to find out. Okay, so I didn't talk about mathematics so far, I admit this. But it is an important observation. So what have we learned? There are about several hundred new readings compared to what Heiberg was capable of doing in 1906 when he didn't have digital enhancement, but before the manuscript was effectively destroyed through the 20th century. So I'm going to share some of this experience. A lot of it is about this experience. What I'm going to talk about, the first thing I want to bring is really not about the contents at all. It's about process, experience, and the sense of what happens when you're studying this. So what are we looking at? Here is a piece of argument where Archimedes discusses method proposition 7, the question, what's the size of a segment of a sphere, which is defined by the height relative to the radius. So here is a segment of a sphere. We want to find the volume. Okay, that's what we're studying. And Archimedes develops an argument for this. And Heiberg reads and reads and reads. I have to explain. So in a way, we, philologers of mathematics, we cheat a lot. Because we have a much easier time than someone who does, say, let's say, philology of Euripides. We know the kinds of things that are going to be there. The text is very formulaic. It must follow a certain mathematical logic. This is what we really use. So this is how you can read it even if you're stuck in 1906 without digital enhancement. Okay? But if you lose the thread of the argument, then you're lost. Okay, that's what happens. So this happened to Heiberg. He got to around here. Here we get to a point where it's very, very legible. You can almost read it with the naked eye right now. But that's about where Heiberg got. Starting here, he couldn't make any sense of it. He lost the thread completely. So for an entire half page, he lost the sense of the argument and he could no longer follow. But we can. This is legible. We can read this now. We know what's going on there. We can recover the sense. We can follow the mathematical argument. And now the page ends, and we move to the next page. The next page does not exist. The next page is lost. The next page had a forgery painted on it. It was sold. Maybe it's hanging somewhere. Maybe it's hanging somewhere in a living room in Europe where people actually still believe that they own a Byzantine illumination that their parents bought, but that's what it is. It's lost to us. We can't read it. So we've lost this. Heiberg had access to the page, but he couldn't read almost anything in it, really just tiny letters here and there. However, here is the beautiful thing about the process. However, he did record what he read. We've got a record of what he read. So here is the record here. Some of it he reads directly, some of it he guesses. The guesses are wrong. The guesses he makes are wrong because he doesn't know what he's talking about. Because remember, he lost the thread even before, right? But he's very careful. He tells us what he actually sees and what he only guesses. So now what we do is we take the letters he actually saw, we remove the guesses, and now we can reinsert. We don't have anything to read from. It's lost. It's a lost page, but we peer through it in a distance of 100 years, reading behind Heiberg's back, seeing what he saw, and being able to fill in the blanks because we know what we're talking about. finally. And now we can get ahead, not right to the end. There's still about half a page beyond this, but now we know what the argument is like, and actually it's different. It's more elegant, it's more beautiful even than what Heiberg has reconstructed. Now we have the actual argument. We have the actual argument of Archimedes thanks to this operation. So this is about, I think you can have a sense of the sheer spine-tingling exercise of communing with so many generations of the dead when you're walking on this, communing with Archimedes and bringing his words back to life for the first time, communing with Heiberg and relying on his wisdom, on his good sense of reporting what he saw and talking to him from 100 years. So that's one thing we did, and this was a fairly legible text. I think I want a somewhat darker auditorium maybe to go through this. It won't help much. This is a difficult set of letters. But maybe you can follow me here. Do you see a theta? If you can, please, try and see a theta. Okay. You get yourself trained. You get yourself trained to see those things, and there's a retina after image that helps too. Here is an omicron. That's actually a very clear, many cases we don't see the letter. However, we see a chunk of a letter which is very inconsistent with many other things. There is this horizontal here. There is no question this comes from an original ink. And when you have lots of experience, you know what comes from the original ink and what doesn't. This could be the end of a sigma. It could also be the end of an epsilon, but this wouldn't make sense after an omicron at all, theta omicron. So it is a sigma, but thos makes lots of sense. This actually is not familiar to you a lot, but we can see the lambda here and then followed by the eta. There is only a smudge left of the plethos. Plethos. We have the word plethos. So that's what you do. Very often, in terms of the amount of time you spend, 90% of the time you work on those 10% of the letters where you need to carve out letter by letter, making sense of them, trying to identify the inks, trying to see what makes sense. Plethos, this is valuable, this is worth it. From the word plethos, we can reconstruct a sentence. So then there is not a small multitude of figures made of them. And this fits a larger puzzle, because we know that Archimedes is at the introduction of a treatise dedicated to an ancient puzzle, and this is all that remains of this treatise, only this introduction. And now we have the key sentence of this introduction. The key sentence of this introduction said, there is not a small multitude of figures made of them. And what was he talking about? So he was talking about this kind of tangram puzzle, stomachion puzzle, where you fit together 14 tiles or 11, because some of them have to be attached to each other. And from other things that he says, we believe that maybe what he was doing is trying to enumerate this plethos, this multitude, the many ways in which you can fit together the square of the stomachion from its components. So we think it's a kind of combinatoric, maybe enumerative project, and it's important because this once again fits another bigger puzzle, a cultural puzzle now. So if we understand the stomachion correctly, it actually fits a general tendency in Greek culture to study the enumeration of big numbers, finding lots of those amazing, gigantic, give me a place and I shall move the earth kind of problems. So give me a place and I shall estimate the size of the universe. Give me a tiny puzzle and I'll show you that there are over 17,000 ways of solving it. This was one of the games that they were playing. And so we understand this game better thanks to the stomachion. It fits more things. And indeed, if they reach for the big, if they reach for big numbers, do they reach for infinity? Well, here's another puzzle. Here we have a big piece, a big missing piece. So Archimedes in the method right at the end, he needs to measure the cylindrical cut. By cylindrical cut, we mean a cylinder that's cut at the base and also cut by a slanted plane passing through the diameter. Okay? So that's what we're looking at, a cylindrical cut, a kind of hoof, a kind of tip of a lipstick object. We want to find the volume of this one. So what we do, and that's typical for the way Archimedes approaches problems in the method, what we're doing is to look for an arbitrary plane passing through this cylindrical cut, parallel to one of the sides. So we have this arbitrary cut. And now we have a fundamental result of proportion, which is derived in pure geometry, and is a very lovely result in its own terms. I show it here. So obviously, this would be the base of the cylinder. We'll have a semicircle here, and we'll have a rectangle on top of it. And we cut a triangle, right? Here is the triangle that is cut from the big cube that holds the cylinder. Here's the triangle that's cut from the cylindrical hoof, because my base is inside the circle, okay? And now what I pass also here, sorry, this is not drawn correctly, what I pass here as well is a particular parabola that touches here. And we have the following property of the parabola. The ratio of the line cut by the rectangle to the line cut by the parabola is as the ratio of the big triangle to the small triangle. That's a very nice geometrical result. It actually means in a way that what it actually means is that the ratio of the rectangle line to the circle line is the same as the ratio from the circle line to the parabolic line, which means that the circle is in a way the exact mean between a straight line and the parabola, if you like to think about it in such terms. So Greeks likes those proportions. It's a lovely result in and of itself. But it immediately makes you think about potential applications, because if the line at the base is to the line of the base, let's expand this dimensionally. So let's say rectangle to the area covered by the parabola as the triangular prism to the cylindrical cut. Now, the area of a parabolic segment was found by Archimedes independently. So area of rectangle to parabolic segment is easy. We can do this. The parabola is already rectified. We know how to measure this. So this means, of course, a triangular prism is already a rectilinear object. We can measure this. So this means that we've measured the cylindrical cut. If we allow ourselves to make the dimensional jump, if we allow ourselves to move from the property line to line as triangle to triangle into the property area to area as solid to solid. This is what we need to do. We need to make it a dimensional jump, an infinitary jump. And the question is, how do we do this? Heiberg didn't know. Here is where Heiberg stood. Here is where the basic geometrical result is achieved with the basic proportions. And here is where the conclusion is made for the solid. And in between these two lines that are marked in green, is this area in Heiberg edition where he can't make heads or tails. He cannot understand this because, once again, the way we read this, mathematical philologists, is by cheating. We read text when we know what's written in them. And Heiberg didn't know what's written in there. He had no idea how this could work, and he said, I just don't know what's in there. He was very clear about this, he was very explicit about this, he left all those dots. But through the 20th century, you know, this gets translated. In the translation, you don't repeat all the dots, and this gets studied. And through the 20th century, people basically forgot about this. So the sense was that Archimedes did this and then did that, and he made a kind of leap of faith. He probably meant some kind of heuristic argument. If it's true in the two-dimensional level, it will be true at the three-dimensional level, and you can expand across all the infinitary cases and in them up together. And now we read this, And we read something very surprising we didn't expect to read. We read there are certain magnitudes equal to each other, the triangles in the prism, and there are other magnitudes which are lines in the parallelogram, delta eta being parallel to kappa theta, which are both equal to each other and equal in multitude. They have the same multitude, the same word, plethos. Things are being equal in multitude to each other. So what is equal to what in multitude? The lines of the type A are equal in multitude to the triangles of type C that are above them. So we have all the cuts. He's very clear about this. He's talking about, otherwise the argument wouldn't work. He talks about all the cuts, all the planar cuts you can make in the solid. If you make all the planar cuts in the solid, the number of the lines in the rectangle is equal to the number of the triangles in the prism. Which we can see, it's a kind of a one-to-one argument. It makes sense. They have the same cardinality, we would say, only that Greeks are not supposed to say such a thing. Greeks are not supposed to say this. This is what I was taught, this is what I taught others. We were taught that the Greeks always avoid actual infinity. They never talk about the number, the multitude of an infinite set. How do we know this? Generally speaking, this is a rule that I would like to offer. When you hear people say the Greeks believe that, what this usually means is Aristotle believed that. And indeed, Aristotle tells you that you should avoid actual infinity. That's true. That's a correct observation about Aristotle. And I think it's true that in general, the Greeks are cautious. They are trying to get rigor. They're trying to have rigorous proofs, so they're cautious about the proofs. But generally speaking, you can say that the Greeks don't agree about stuff. So if one Greek believes that you should always avoid actual infinity, it's actually not that surprising to find that there is another Greek who plays with actual infinity, and he tries to apply here a general argument about how you can sum up proportions and tries to extend it to an infinitary case. I'm not sure that the argument is valid. There are problems with this extension, but the effort, this is directly suggestive in some ways of the 17th century, in other ways even in the 19th century in terms of thinking about the equality in multitude of infinite sets. So that's a very remarkable moment. And the next one, the final one that I want to talk about, this is one where it really was hidden in plain sight. It was there. And I keep talking about Heiberg and repeating my admiration to him. I say we philologists cheat. I cheat more than others because I rely on Heiberg. Fundamentally, the way I managed to read this is thanks to the fact that Heiberg read it already. I have no idea how I would have done it without his aid. Here is one point where I do criticize him, however. He never looked at the diagrams. He thought, okay, those are diagrams and they look somewhat wrong, and I don't believe in them. And anyway, I'm a philologer. You know what philologer is. A philologer is someone who loves words, who loves logos. So they copy words. They try to find words. They were not trained to study diagrams. So they never copied the diagrams. They never studied the diagrams. And I think the diagrams are important. They tell us important things about the way you think mathematically. And here is an important moment of mathematics, I think. I tell you, Archimedes does all those foundational things. He really begins physics. He really begins mathematical physics. And this is the moment of the beginning, the first actual proof, the first actual argument of floating bodies, the main piece of hydrostatics, the real crown of Archimedes' achievement. So this is really where the scientific revolution would start from. So floating bodies, book 1, proposition 8. What are we looking at? So I need to explain what we're looking at. We're looking first of all at the ocean. For clarification, for the sake of these hydrostatics, we assume that there's only liquid. We idealize and we get rid of Earth. There's a liquid Earth that we're looking at. Also, no one in antiquity doubts, of course, and very few would doubt even through the Middle Ages, that the Earth is spherical. So we know this. The Earth is spherical and it is liquid. And here we have a vessel, a very big vessel, immersed in the ocean. We don't try to scale things, obviously. So here is a vessel. And here is, it's specifically a spherical segment. We're taking the case of a spherical segment bigger than a hemisphere, and this is the center of the sphere, kappa. Here is the center of the Earth, lambda. And this gives rise to a question. Why is the center of the Earth eccentric? So once again, it's a piece of the puzzle, and it fits a larger puzzle. We can look at other things. Here is Euclid's Elements, Book 3, Proposition 13. It's a proof by contradiction. You assume something, you show a certain absurdity, and therefore you show that the assumption was wrong. In this case, you assume you want to show that a circle does not touch another at 2 points. Okay, let's try and have a circle touch another at 2 points. Here is what we have in the ancient manuscripts. This crescent stands for a circle. In modern treatments, what you're doing is the thing that looks most like a circle. You will have a flat tire instead. In the ancient diagrams, you don't have a flat tire, you have a crescent, a very obvious non-circle. Here is another case from Archimedes himself, spiral lines 13. The argument is that, once again, it's very similar. A tangent does not touch a spiral at 2 points. Okay, let's assume that a tangent does touch a spiral at 2 points. This is a line, okay? This thing from epsilon to zeta is a straight line. A single straight line. You follow me, right? It's a straight line, but it's broken. It's broken. It's the most manifestly non-straight line that you can imagine, and this is the rule. So it fits a larger pattern. In proofs by contradiction, the absurdity of the diagram is made manifest. This is different from the modern treatment, but you see, if you're studying ancient diagrams, you find things, you find certain patterns, you find certain ways of thought. What they do is to emphasize the absurdity of the situation in proofs by contradiction. So this is a proof by contradiction, I believe. This was not obvious. The diagram helps us, but when you look at it in this way, you can realize that the text itself suggests a proof by contradiction. It wasn't obvious because it doesn't look like it should be or can be a proof by contradiction. What goes on? Archimedes wants to show that the figure, the spherical segment, comes to a stand upright in such a way so that the axis of the segment is along a perpendicular, we can say pointing towards the center of the Earth. If you take a spherical segment, no matter how you position it, inclined or not inclined, it would come to a stand upright. You can try it in the bathtub if you have an appropriate spherical segment at home, and you can see that it actually works. It will balance itself in this way. So that's what we're trying to show. And how does the proof work? It says, let the figure, if possible, be inclined. As if it was an argument by contradiction. Let's assume against, absurdly, that the figure is inclined. This is how you show it, and you show it in a completely schematic, arbitrary way, and you're not showing an inclined figure, it's not even shown inclined. What you're showing is an eccentric Earth. And then what happens? What happens is that the centers of gravity within the liquid, outside the liquid, are not aligned. Because they're not aligned, the figure would rotate. So this is how you show that the figure will be unstable at this particular arrangement. If it's not at a perpendicular, it will be unstable. This is what you actually prove. This is what Archimedes achieves. And then he says, it is clear that the figure should not rest, by its parts that epsilon will be carried downward until zeta theta comes to be along a perpendicular. The argument is, let us assume the segment is stable at a position non-x. We obtain instability. It is therefore not stable at position non-x, and it will reach stability at position x. This is where you reach stability. Now, I'm not denying that position x is stable. The two centers of gravity are indeed aligned, and they will cancel each other out, and the figure will be stable. I follow this argument. The argument is valid. I have to explain. Let's be clear. Archimedes' floating bodies is still the starting point of hydrostatics. When we do fluid dynamics today, we start with Archimedes. It's valid. It's a subset of science that works. But the argument here has an interesting lacuna. The lacuna is not about the fact that when you reach stability, it's actually stable. The lacuna is about the argument of a path, the implication of a path. You start from the unstable position, You show that it's not stable, and from this you derive the stability at the position of stability. But Archimedes actually is incapable of showing what will happen next. He's not trying even to calculate what will be the position a moment later. This is not what he's doing. He's jumping between two snapshots in time. And this is not entirely valid because, of course, it's completely conceivable, and Archimedes was perfectly aware of this, that we'll have some kind of an asymptotic arrangement where you never reach the end point. There are lots of such arrangements in Greek geometry. He should have been aware of this possibility. I'm sure he was aware of this possibility, but this is not how he thought about this. And this, I think, is a deep moment for thinking about where mathematical physics comes from. So obviously it comes from an idealization. It comes from thinking about the Earth as a sphere, about pure liquid, about objects which are purely geometrical, purely homogeneous, but there's something even more. The very logic of the situation you think about when you're thinking about mathematical physics, when you make this first step, you're thinking in terms of the logic that you're familiar with from geometry, a logic of logical states that does not demand physical paths. There isn't a physical path because there is truth here, falsehood there, and this is how you make your transitions in Greek mathematics. Mathematical physics is created, I would say, as mathematics through and through. So that's an important observation, I think, and we get it out of this diagram, we get it out of this eccentric center, we get it out of this piece. So as I said, quite a number of pieces of the puzzle, the nature of the Byzantine tradition, we find a scriptorium in Jerusalem, we read behind Heiberg's back, we find about big numbers in Hellenistic mathematics, we find actual infinity even, and we find something about the origin of mathematical physics. So you get the sense of the excitement and my gratitude for you coming here today to hear about this excitement that I shared. Thanks. The object. We have another source for the stomachion, which is an Arabic manuscript. This Arabic manuscript does not overlap at all with the Greek text. It's only a single statement, and this single statement provides a construction of an object that it calls the stomachion. It fits because it has 14 pieces. We hear from other ancient sources that there was a game that involved, in fact, 14 pieces. So once again, you put those pieces of the puzzle together and you think maybe it does fit. Maybe it's no. There is a question about this. There is a debate about the precise shape of the stomachion. The actual diagram that we do have in the stomachion from the very first proposition involves not a square, but a rectangle in the ratio of 2 to 1. Maybe it's a double stomachion, maybe it's something else. It's not clear. But I don't know how much should be made of this. Archimedes often writes in sly, surprising ways, and it's very, very typical to have a couple of propositions right at the beginning that suggest the subject matter, but do not directly address it, and you only find afterwards how they meet the subject matter at hand. So there are all sorts of possibilities there. We are looking at the dark, trying to fit those pieces. Probably that's how they fit.
So you alluded to sort of using a frequency analysis in some sense to help you decode maybe letters that are next to each other but are not very like layers.
Yeah. We do those things effectively.
Are cryptanalysis sort of ideas that kind of played a role into it, or is it really much more of an art to kind of decipher what the text really is saying?
Right. No, I think it is fundamentally doable. And one of the projects that were developed, I didn't talk about this. This is not something I'm much of an expert on. But there was a whole group of imaging scientists working on this. And there were studies coming out of this scientific research done on this. And there was, I think this was in fact primarily a master's thesis, though it got published too. That try to create a paleographic tool that learns the letters of this palimpsest and compares them and produces a ranking of probabilities. It didn't get to the point that it was a major tool other than a toy, partly because at the end we're talking about, I don't know, 100,000 characters in total in the entire manuscript, but it's doable, and the script is fairly, this also helps. I should say that the script is not, it's not a very lavish manuscript, but it's a very professional one, and the professional scribe does things very solidly, very predictably. So there are 3 or 4 ways to do a particular letter, but not more than this. So you can build a library in your head and you compare this library, but there are all sorts of probabilistic argument. I talked about, I should clarify this thing. So, so when we're looking at this letter, you might have wondered, as I was talking, why this manuscript was written in red, and wasn't it distracting to the people who read the prayer book? But it's not, okay? It's, first of all, we don't have, the original ink is largely gone. What we have is the reaction of the original ink with the parchment, because the ink was mostly removed in the scraping. And this is a kind of a faint orangish thing. And the digital enhancement picks up the typical properties across several wavelengths, particularly ultraviolet. Typically ultraviolet does the work that react where this particular chemical reacts particularly well, and it transforms this into this marked red, which stands out more clearly. And however, it will do this to some extent to anything that behaves like this across the wavelengths. It's just an algorithm that works on wavelengths. So you begin to develop intuitions about, is this red deep enough, characteristic enough to be thought of as coming out of an actual writing? Is it the kind of reddish blob that is simply part of the skin? So this is what you get to develop as a second sense through several months of working on this. I teach students this, and through the semester they get to the point that they can have a good sense of what are letters, what are not.
You mentioned how surprising it was to find Archimedes using the concept of infinite numbers. Would you say that it's unique in ancient Greek manuscripts?
Well, once you look at it this way, you begin to notice other things. There's another passage that's attributed to Archimedes where it's much vaguer, but we have a report, not the original text. In this report, it seems like Archimedes was saying something along the lines that the number of radial lines projecting from the center onto a spiral in a single rotation is associated with the number of circles constituting a cone by a particular arrangement. So maybe he did some kind of work like this elsewhere. It's not clear if anyone else really followed this particular line of argument. In general, it's not as if Archimedes had many followers in antiquity. It is this moment of flourishing which is not really repeated until Galileo, really, to a large extent. Mm-hmm.
So you said for one of the missing pages, you have hyper translation of what he read.
Yeah.
Not translation, but
Transcription, yeah.
Do you have his transcription for all of the missing pages?
Well, we have his transcription for everything he could read back then. But it does so happen, there are 3 missing pages. One of them is very solid. We know what's in there. We don't worry too much. In fact, it's also covered by Codex A. So this is one of the cases where it overlaps with a different manuscript, so we're not in trouble there at all. There are 2 pages that are taken from this work, the method, which exists only on the Palimpsest. We don't have anything comparable, and they are poorly documented by Heiberg. So these are major losses. Yeah. So yeah, this is indeed a tragedy, and indeed I hope that someone will turn over their forgery in their living room.
So the word for multitude in that one proof, is it
Plethos.
in the Greek, is it the same word that philosophers use to talk about like the infinity of the universe in a qualitative sense, or is it a different word just means
There are all sorts of words, but the word you have in mind is apeiron, which means infinity, and that's not what we have here. And it's not at issue at all, and you basically don't find this but you know, the deep point really for this particular set of authors in the 3rd century, they did mathematics, they did not do philosophy. And that's something typical of Hellenistic mathematics. It's not typical of what goes on before them in the classical era. But there is this moment, this brief moment. Once again, we're talking about a brief moment where science is done apart from philosophy. You lose certain things. When Galileo does it again and thinks about all those things philosophically, there are lots of insights that you generate, but you gain certain things. You think more precisely, you don't worry too much about the physical interpretation. You just do this pure mathematical game, and paradoxically, by doing the pure mathematical game, you get the physics right somehow. So really, in a way, and there is a reason why it happens. It happens in the 3rd century BC, because in the 3rd century BC, the world bifurcates for a time between 2 centers, Athens and Alexandria. Athens is where people do philosophy. Alexandria is where people do all the rest. Archimedes, of course, lives in Syracuse, but Alexandria is where he's really addressing himself. He belongs to a scientific world. He belongs to a world where science is not philosophical, and I think it's the first scientific society. It's the first flourishing of science, where science is done in a constrained, restricted way, which is extremely powerful.
Do you think it's more a factor of history or of Archimedes' personal talent that he was such an isolated incident of talent that no one seemed to be able to follow after?
Right. So what goes on? What goes on in the year 200 BC after Archimedes dies? It's not precisely that no one goes on after him. It's a kind of a generational event. So there's Archimedes, there are all those people who communicate with him, there's a few people who continue working after his death, and then this more or less dies out, this phenomenon. What I would say is this: we live in a very special kind of institution. We work, all of us, we belong to universities. We belong to institutions that have long continuities, and you inscribe all those names at the floors here at the University of Arkansas. I keep looking at those names and reading those names. It's amazing. So, and the thing is, you didn't have this before the Middle Ages, and in some ways you didn't have those institutions contributing to science the way we think about it before the 18th century, let's say. You didn't have those continuous projects impersonal projects of doing science. That's something which is very modern. And I think this is what typically you find in the pre-modern world. Those kinds of creative moments are moments. They are generational phenomena. And you have lots of generational phenomena. So I think we, shoe is on the other foot. The question is not why do people end doing something. It's the most natural thing that after you get excited about something, the group of people who were excited about something would die out and then it will be over, obviously. The really interesting question is how you manage to preserve culture impersonally, so that generation after generation, people will continue banging against the very same problems and achieve this fantastic progress of science that we now take for granted. And this is something that has been achieved by the university, I think, and never really established before that.
Sure, for further questions, Dr. Netz will be happy to answer.